Welcome to a new session of Advanced Calculus. In this unit, we discuss two topics. First one titled Taylor's Theorem for Functions of Two Variables, and the other one titled the Jacobians. Let us start with the Taylor's Theorem. The results for two variable functions can be obtained by applying single variable calculus to them in a special environment. An easy way to do this is to build single variable function F of t by combining two variable function f of xy with parameterized paths x of t and y of t. Taylor's theorem for single variable function says that a function f of x can be approximated by polynomials near a given point. Here we attempt to derive the two variable version of Taylor's theorem from the one variable case. For a function F of t, one variable Taylor's theorem gives an approximation at t0 as F of t equal to F of t0 plus F dash of t0 times t minus t0 plus r1, where r1 is the corresponding remainder. This linear approximation fits F of t with a straight line through t0. Consider a function f of xy and a base point ab. Choose a nearby point a plus h b plus k in the domain of definition of f of xy. Take the straight line segment joining a plus h b plus k to ab. We parameterize the equation of this line segment as x of t equal to a plus th, y of t equal to b plus tk, where 0 less than or equal to t less than or equal to 1. When t equal to 0, we have the point ab, and when t equal to 1, the point a plus h b plus k. Define F of t equal to f of x of t, y of t. Then F of 0 equal to f of ab, and F of 1 equal to f of a plus h b plus k. Now Taylor's approximation of F of t with t0 equal to 0 and t equal to 1 becomes F of 1 equal to F of 0 plus F dash of 0 plus r1. We change the above expression to the original function f. The evaluation of the derivatives of f of xy can be done using chain rules. In this way, the Taylor's polynomial of f of xy in the first order case can be obtained. Similar derivations can be done to obtain Taylor's polynomials and remainders containing any order of derivatives. Taylor's theorem. If a function f of xy of two independent variables x and y possesses continuous partial derivatives of order n in any domain E of a point ab, and if a plus h b plus k is any point of E, then there exists a positive number 0 less than theta less than 1 such that f of a plus h b plus k equal to f of ab plus D f of ab plus 1 by 2 factorial D square f of ab plus etc. plus 1 by n minus 1 factorial D raised to n minus 1 f of ab plus rn, where D equivalent to h del by del x plus k del by del y, and rn equal to 1 by n factorial D raised to n f of a plus theta h b plus theta k 0 less than theta less than 1. Proof. Let x equal to a plus th, y equal to b plus tk, where 0 less than or equal to t less than or equal to 1 is a parameter, and F of t equal to f of xy, which is equal to f of a plus th b plus tk. Since the partial derivatives of f of xy of order n are continuous in the domain, the nth derivative F raised to n of t of composite function F of t is continuous in closed interval 0 1. Also, F dash of t equal to df by dt equal to del f by del x times dx by dt plus del f by del y times dy by dt, which is equal to h times del f by del x plus k times del f by del y, which is equal to h del by del x plus k del by del y of f, which is equal to df. F square t equal to d by dt of h del f by del x plus k del f by del y, which is equal to del by del x of h del f by del x plus k del f by del y times dx by dt plus del by del y of h del f by del x plus k del f by del y times dy by dt, which is equal to h del square f by del x square plus k del square f by del x del y times h plus h del square f by del y del x plus k del square f by del y square times k, which is equal to h square del square f by del x square plus 2hk del square f by del x del y plus k square del square f by del y square, which is equal to h del by del x plus k del by del y whole square f equal to capital D square f. Similarly, capital F cube of t equal to capital D cube f and so on. In general, capital F raised to n of t equal to capital D raised to n f. Now, for t equal to 0, f of x y equal to f of a b. Applying Maclaurin's theorem for the function capital F of t on closed interval 0 1, we get capital F of t equal to capital F of 0 plus t times capital F dash of 0 plus t square by 2 factorial capital F square of 0 plus etc. plus t raised to n minus 1 by n minus 1 factorial capital F raised to n minus 1 of 0 plus t raised to n by n factorial capital F raised to n of theta t, where 0 less than theta less than 1. Now, putting t equal to 1, we obtain capital F of 1 equal to capital F of 0 plus capital F dash of 0 plus 1 by 2 factorial capital F square of 0 plus etc. plus 1 by n minus 1 factorial capital F raised to n minus 1 of 0 plus 1 by n factorial capital F raised to n of theta, where 0 less than theta less than 1. But capital F of 1 equal to f of a plus h b plus k, capital F of 0 equal to f of a b, capital F dash of 0 equal to capital D f of a b, capital F square of 0 equal to capital D square f of a b, etc. and capital F raised to n theta equal to capital D raised to n f of a plus theta h b plus theta k. Substituting these values in the expression of capital F of 1, we get the following: f of a plus h b plus k equal to f of a b plus capital D f of a b plus 1 by 2 factorial capital D square f of a b plus etc. plus 1 by n minus 1 factorial capital D raised to n minus 1 f of a b plus 1 by n factorial capital D raised to n f of a plus theta h b plus theta k, where 0 less than theta less than 1, which is equal to f of a b plus capital D f of a b plus 1 by 2 factorial capital D square f of a b plus etc. plus 1 by n minus 1 factorial capital D raised to n minus 1 f of a b plus Rn, where Rn equal to 1 by n factorial h del by del x plus k del by del y whole raised to n f of a plus theta h b plus theta k, 0 less than theta less than 1, which is called the remainder after n terms. This completes the proof of Taylor's theorem for function of two variables. Another form of Taylor's theorem: put a plus h equal to x, b plus k equal to y, then h equal to x minus a and k equal to y minus b in Taylor's theorem, and it takes the form f of x y equal to f of a b plus capital D f of a b plus 1 by 2 factorial capital D square f of a b plus etc. plus 1 by n minus 1 factorial capital D raised to n minus 1 f of a b plus Rn, where capital D equivalent to h del by del x plus k del by del y, which is equivalent to x minus a del by del x plus y minus b del by del y, and Rn equal to 1 by n factorial x minus a del by del x plus y minus b del by del y whole raised to n f of a plus x minus a theta b plus y minus b theta, 0 less than theta less than 1. This gives the Taylor's expansion of f of x y about the point a b in powers of x minus a and y minus b. Example: let us find the expansion of f of x y equal to x square plus xy plus y square in powers of x minus 2 and y minus 3. Capital df equal to h del f by del x plus k del f by del y, which is equal to h fx plus k fy. Capital D square f equal to h square del square f by del x square plus 2hk del square f by del x del y plus k square del square fy del y square, which is equal to h square fxx plus 2hk fxy plus k square fyy. Capital D cube f equal to h cube fxxx plus 3h square k fxxy plus 3hk square fxyy plus k cube fyy. Here the base point is AB equal to 2, 3. Then h equal to x minus 2, k equal to y minus 3. F of 2, 3 equal to 2 square plus 2 times 3 plus 3 square, which is equal to 19. Fx equal to 2x plus y implies that fx of 2, 3 equal to 7 and fy equal to x plus 2y gives fy of 2, 3 equal to 8. Similarly, fxx of 2, 3 equal to 2, fxy of 2, 3 equal to 1, fyy of 2, 3 equal to 2 and f(x) equal to 0, fxxy equal to 0, fyyx equal to 0, f(y) equal to 0. All other higher order partial derivatives vanish at 2, 3. Hence, from Taylor's theorem, f of xy equal to f of 2, 3 plus capital D f of 2, 3 plus 1 by 2 factorial capital D square f of 2, 3 plus etc. plus 1 by n minus 1 factorial capital D raised to n minus 1 f of 2, 3 plus Rn, which is equal to 19 plus x minus 2 times 7 plus y minus 3 times 8 plus 1 by 2 factorial times x minus 2 whole square times 2 plus 2 times x minus 2 into y minus 3 plus y minus 3 whole square times 2, which is equal to x minus 2 whole square plus y minus 3 whole square plus x minus 2 into y minus 3 plus 7 times x minus 2 plus 8 times y minus 3 plus 19. Maclaurin's expansion in finite form. If we put a equal to 0, b equal to 0, h equal to x, k equal to y in Taylor's theorem, it takes the form f of xy equal to f of 0, 0 plus capital D f of 0, 0 plus 1 by 2 factorial capital D square f of 0, 0 plus etc. plus 1 by n minus 1 factorial capital D raised to n minus 1 f of 0, 0 plus Rn, where capital D equivalent to x d by dx plus y d by dy and Rn equal to 1 by n factorial capital D raised to n f of theta x theta y 0 less than theta less than 1. This is the Maclaurin expansion in finite form. Now we pass through the topic titled the Jacobians. A function given explicitly in the form y equal to f of x of single independent variable x can be easily differentiated to find dy by dx. Suppose we are asked to find the derivative of x equal to 1 by root of 1 plus y square with respect to x. The calculations may be easier if we find dx by dy first. Now the required derivative dy by dx equal to dx by dy whole raised to minus 1, the reciprocal of dx by dy. The change of variable is a basic tool used to simplify the calculations in given problems. If the independent variable x in y equal to f of x is changed to another variable t using x equal to phi of t, the derivative is obtained from dy by dx equal to dy by dt times dt by dx, which is equal to dy by dt times dx by dt whole raised to minus 1. In problems involving functions of two variables, the process of change of variable is done using different transformations. Suppose z equal to f of uv is a function of two independent variables u and v. A substitution of u equal to phi of xy and v equal to psi of xy is applied to introduce the new independent variables x and y. We are asked to express the derivative of z with respect to u and v in terms of x, y, del z by del x and del z by del y. After transformation, the given z will become a function of x and y. Applying chain rule, we have del z by del x equal to del z by del u times del u by del x plus del z by del v times del v by del x. Del z by del y equal to del z by del u times del u by del y plus del z by del v times del v by del y. Solving for del z by del u and del z by del v, we obtain del z by del u equal to capital A times del z by del x plus capital B times del z by del y del z by del v equal to capital C times del z by del x plus capital D times del z by del y, where capital A, B, C and capital D are given by the expressions capital J equal to determinant first row del u by del x del u by del y, second row del v by del x del v by del y, and capital J A equal to del v by del y, capital J B equal to negative del v by del x, capital J C equal to negative del u by del y, capital J D equal to del u by del x. We can observe the effective role of aforementioned determinant capital J in change of variables from the following geometrical interpretations. There are problems in which calculations depend on the region described by the domain of the function. When the calculations become difficult, we may search for a nicer region to work with. For example, consider region R described by the independent variables u and v given by straight lines u equal to 1, v equal to u, v equal to minus 2u. Figure 1 gives the region R. Plugging the transformation u equal to x plus y, v equal to y minus 2x into the given equations, we obtain the region capital G as in figure 2 bounded by x plus y equal to 1, x equal to 0, y equal to 0. It is again a triangle but a nicer one to deal with. Area of capital R equal to 3 by 2 square units. Here capital J equal to determinant first row 1 1, second row negative 2 1 which is equal to 3. Area of capital G equal to half square units. Therefore, area of capital R equal to J times area of G. The determinant capital J that plays a vital role in the transformations is called a Jacobian determinant, often called the Jacobian, named after the German mathematician Carl Gustav Jacobi. The Jacobian. If u1, u2, etc. un are differentiable function of independent variables x1, x2, etc. xn, then the determinant first row del u1 by del x1, del u1 by del x2, etc. del u1 by del xn, second row del u2 by del x1, del u2 by del x2, etc. del u2 by del xn, etc. etc. nth row del un by del x1, del un by del x2, etc. del un by del xn is called the Jacobian of u1, u2, etc. un with respect to the independent variables x1, x2, etc. xn and is denoted by capital J equal to del of u1, u2, etc. un over del of x1, x2, etc. xn or capital J of u1, etc. un over x1, etc. xn. Let us see a couple of examples. Jacobian of two independent variables. Let u equal to x times 1 plus y and v equal to y times 1 plus x. Capital J of uv over xy equal to del of uv over del of xy equal to determinant first row del u by del x, del u by del y, second row del v by del x, del v by del y. Here del u by del x equal to 1 plus y, del u by del y equal to x, del v by del x equal to y, del v by del y equal to 1 plus x. Then the Jacobian del of uv over del of xy equal to determinant first row 1 plus y x, second row y 1 plus x which is equal to 1 plus y times 1 plus x minus xy equal to 1 plus x plus y. Jacobian of three independent variables. Let u equal to x square plus y square plus z square, v equal to x plus y plus z, w equal to xy plus yz plus zx. Del u by del x equal to 2x, del u by del y equal to 2y, del u by del z equal to 2z, del v by del x equal to 1, del v by del y equal to 1, del v by del z equal to 1, del w by del x equal to y plus z, del w by del y equal to z plus x, del w by del z equal to x plus y. The Jacobian capital J of uvw over xyz equal to del of uvw over del of xyz equal to determinant first row del u by del x, del u by del y, del u by del z, second row del v by del x, del v by del y, del v by del z, third row del w by del x, del w by del y, del w by del z which is equal to determinant first row 2x, 2y, 2z, second row 1, 1, 1, third row y plus z, z plus x, x plus y, which is equal to 2x times y minus z plus 2y times z minus x plus 2z times x minus y equal to 0. Here v square equal to x plus y plus z whole square, which is equal to x square plus y square plus z square plus 2xy plus 2yz plus 2zx, which is equal to u plus 2w. Therefore, v square minus u minus 2w equal to 0. This gives a relation between u, v and w, that is, they are not independent. Theorem: if a function u, v, w of three independent variables x, y, z are not independent, then the Jacobian of u, v, w with respect to x, y, z vanishes. Proof: it is given that u, v and w are not independent, so there must exist a relation connecting them. Let it be capital F of u, v, w equal to 0. Differentiating this relation with respect to x, y and z using chain rule, we get del capital F by del u times del u by del x plus del capital F by del v times del v by del x plus del capital F by del w times del w by del x equal to 0. Del capital F by del u times del u by del y plus del capital F by del v times del v by del y plus del capital F by del w times del w by del y equal to 0. Del capital F by del u times del u by del z plus del capital F by del v times del v by del z plus del capital F by del w times del w by del z equal to 0. Eliminating del capital F by del u, del capital F by del v and del capital F by del w from these equations, we have determinant first row del u by del x, del v by del x, del w by del x, second row del u by del y, del v by del y, del w by del y, third row del u by del z, del v by del z, del w by del z equal to 0. That is, determinant first row del u by del x, del u by del y, del u by del z, second row del v by del x, del v by del y, del v by del z, third row del w by del x, del w by del y, del w by del z equal to 0. Therefore, the Jacobian capital J of u, v, w over x, y, z equal to 0. Properties of Jacobians. The Jacobians have the remarkable properties of behaving like the derivative of function of one variable. A few of such important results are given here. Theorem 1. If u1, u2, u3 are functions of y1, y2, y3 and y1, y2, y3 are functions of x1, x2, x3, then capital J of u1, u2, u3 over x1, x2, x3 equal to capital J of u1, u2, u3 over y1, y2, y3 times capital J of y1, y2, y3 over x1, x2, x3. Proof. By the rule for the derivative of function of a function, we have del u1 by del x1 equal to del u1 by del y1 times del y1 by del x1 plus del u1 by del y2 times del y2 by del x1 plus del u1 by del y3 times del y3 by del x1, which is equal to sigma k equal to 1 to 3 del u1 by del yk times del yk by del x1. Similarly, del u1 by del x2 equal to sigma k equal to 1 to 3 del u1 by del yk times del yk by del x2. Del u1 by del x3 equal to sigma k equal to 1 to 3 del u1 by del yk times del yk by del x3 and so on. In general, del ur by del xs equal to sigma k equal to 1 to 3 del ur by del yk times del yk by del xs r equal to 1 2 3 and s equal to 1 2 3. Since the Jacobian is a determinant, the row by column rule of multiplication shows that J of u1, u2, u3 over y1, y2, y3 times J of y1, y2, y3 over x1, x2, x3 equal to determinant first row del u1 by del y1, del u1 by del y2, del u1 by del y3, second row del u2 by del y1, del u2 by del y2, del u2 by del y3, third row del u3 by del y1, del u3 by del y2, del u3 by del y3 times determinant first row del y1 by del x1, del y1 by del x2, del y1 by del x3. Second row, del y2 by del x1, del y2 by del x2, del y2 by del x3. Third row, del y3 by del x1, del y3 by del x2, del y3 by del x3, which is equal to determinant first row, sigma del u1 by del yk times del yk by del x1, sigma del u1 by del yk times del yk by del x2, sigma del u1 by del yk times del yk by del x3. Second row, sigma del u2 by del yk times del yk by del x1, sigma del u2 by del yk times del yk by del x2, sigma del u2 by del yk times del yk by del x3. Third row, sigma del u3 by del yk times del yk by del x1, sigma del u3 by del yk times del yk by del x2, sigma del u3 by del yk times del yk by del x3, which is equal to determinant first row, del u1 by del x1, del u1 by del x2, del u1 by del x3. Second row, del u2 by del x1, del u2 by del x2, del u2 by del x3. Third row, del u3 by del x1, del u3 by del x2, del u3 by del x3, which is equal to j of u1, u2, u3 over x1, x2, x3. Generalization. If u1, u2, etc. un are functions of y1, y2, etc. yn, and y1, y2, etc. yn are themselves functions of x1, x2, etc. xn, then capital J of u1, etc. un over x1, etc. xn equal to capital J of u1, etc. un over y1, etc. yn times capital J of y1, etc. yn over x1, etc. xn. Corollary. If xr equal to ur for r equal to 1, 2, 3, etc. n in the theorem, and assuming that the equations which define y1, y2, etc. yn as functions of x1, x2, etc. xn determine x1, x2, etc. xn as functions of y1, y2, etc. yn, then capital J of x1, etc. xn over y1, y2, etc. yn times capital J of y1, etc. yn over x1, etc. xn equal to 1. Proof. By the property of partial differentiation, del xr by del xs equal to 0 if r not equal to s, 1 if r equal to s. Then from previous theorem it follows that capital J of x1, etc. xn over y1, etc. yn times J of y1, etc. yn over x1, etc. xn equal to capital J of x1, etc. xn over x1, etc. xn, which is equal to determinant first row, del x1 by del x1, del x1 by del x2, etc. del x1 by del xn. Second row, del x2 by del x1, del x2 by del x2, etc. del x2 by del xn, etc. etc. Nth row, del xn by del x1, del xn by del x2, etc. del xn by del xn, is equal to determine 1, 0, etc. 0. Second row 0, 1, etc. 0, etc. etc. Last row 0, 0, etc. 1, which is equal to 1. This proves the corollary. The above result may be regarded as generalization of the result dx by dy times dy by dx equal to 1. Let us see another property. Consider y1 equal to x1, y2 equal to x1 plus x2, etc. and yn equal to x1 plus x2 plus etc. plus xn. Here yi is taken as function of x1, x2, etc. xi. The partial derivatives take the values del y1 by del x1 equal to 1, del y1 by del x2 equal to 0, etc. del y1 by del xn equal to 0, del y2 by del x1 equal to 1, del y2 by del x2 equal to 1, del y2 by del x3 equal to 0, etc. del y2 by del xn equal to 0, etc. etc. del yn by del x1 equal to 1, del yn by del x2 equal to 1, etc. del yn by del xn equal to 1. Thus, the Jacobian j of y1, etc. yn over x1, etc. xn equal to determinant first row 1, 0, etc. 0, second row 1, 1, etc. 0, etc. etc. last row 1, 1, etc. 1, which is equal to 1, which is equal to del y1 by del x1 times del y2 by del x2 times etc. del yn by del xn. Here the Jacobian is the determinant of a lower triangular matrix and the value reduces to the product of the diagonal elements. A generalization of this property can be stated as follows. Theorem. If functions u1, etc. un are of the form u1 equal to f1 of x1, u2 equal to f2 of x1, x2, etc. un equal to fn of x1, x2, etc. xn, then capital J of u1 etc. un over x1 etc. xn equal to del u1 by del x1 times del u2 by del x2 times etc. del un by del xn. The Jacobian of implicit functions. Let u1, u2 etc. un, instead of being given explicitly in terms of x1, x2 etc. xn, be connected by equations capital Fy of u1, u2 etc. un, x1, x2 etc. xn equal to 0 for I equal to 1, 2, 3 etc. n. In this case, u1, u2 etc. un may be regarded as implicit functions of x1, x2 etc. xn. The Jacobian of such functions can be evaluated using the following result. Theorem: if u1, u2 etc. un are functions of n independent variables x1, x2 etc. xn given by the implicit relations capital Fy of u1, u2 etc. un, x1, x2 etc. xn equal to 0 for I equal to 1, 2, 3 etc. n, then capital J of u1 etc. un over x1 etc. xn equal to negative 1 raised to n capital J of capital F1 etc. capital Fn over x1 etc. xn divided by capital J of capital F1 etc. capital Fn over u1 etc. un. Proof: differentiating f1 equal to 0 partially with respect to x1, we obtain del f1 by del x1 plus del f1 by del u1 by del x1 plus del f1 by del u2 by del x1 plus etc. plus del f1 by del un by del x1 equal to 0. Therefore, sigma r equal to 1 to n del f1 by del ur by del x1 equal to negative del f1 by del x1. In general, differentiating capital Fy equal to 0 partially with respect to xj for I equal to 1, 2, 3 etc. n and j equal to 1, 2, 3 etc. n, we get sigma r equal to 1 to n del capital Fy by del ur times del ur by del xj equal to negative del capital Fy by del xj for all I equal to 1, 2, 3 etc. n and j equal to 1, 2, 3 etc. n. Now, capital J of capital F1 etc. Fn over u1 etc. un times capital J of u1 etc. un over x1 etc. xn equal to determinant first row del capital F1 by del u1 etc. del capital F1 by del un etc. nth row del capital Fn by del u1 etc. del capital Fn by del un times determinant del u1 by del x1 etc. del u1 by del xn etc. nth row del un by del x1 etc. del un by del xn, which is equal to determinant sigma r equal to 1 to n del capital F1 by del ur times del ur by del x1 etc. sigma r equal to 1 to n del capital F1 by del ur times del ur by del xn etc. nth row sigma r equal to 1 to n del capital Fn by del ur times del ur by del x1 etc. sigma r equal to 1 to n del capital Fn by del ur times del ur by del xn. Substituting the values of each summation equal to determinant first row negative 1 times del capital F1 by del x1 etc. negative 1 times del capital F1 by del xn etc. nth row negative 1 times del capital Fn by del x1 etc. negative 1 times del capital Fn by del xn, which is equal to negative 1 raised to n determinant first row del capital F1 by del x1 etc. del capital F1 by del xn etc. nth row del capital Fn by del x1 etc. del capital Fn by del xn, which is equal to negative 1 raised to n capital J of capital F1 etc. Fn over x1 etc. xn. This completes the proof. Note: the above result resembles dy by dx equal to negative times del f by del x divided by del f by del y, where x and y are connected by the equation f of xy equal to 0. In this unit, we discussed the Taylor's theorem for functions of two variables and the Jacobians. We have presented these topics with the important results and examples. Before we move to the next session, please try to answer the following questions. 1. Using Taylor's theorem, expand x square y plus 3y minus 2 in powers of x minus 1 and y plus 2. 2. If f of xy equal to e raised to x plus y, find Taylor's expansion at the point 0, 0 for n equal to 3. 3. If x equal to r sin theta cos phi, y equal to r sin theta sin phi, z equal to r cos theta, find the Jacobian of x, y and z with respect to r, theta and phi. 4. If u, v and w are roots of the equation lambda minus x whole cube plus lambda minus y whole cube plus lambda minus z whole cube equal to 0, in lambda find capital J of u, v, w over x, y, z. I hope you enjoyed this session. We will be back with another topic. Until then, goodbye.